One of the problems that we have, however, is when working out probabilities, it's not too difficult to take these results and work out the probabilities of one event occurring, etc. But real life can be a lot more complicated than this. And instead of just having the probability of event X occurring, that might be tied in with the probability of something else occurring at the same time. And to work out exactly what's going to happen here can be quite complicated. What we can therefore use is a technique called Monte Carlo simulation. And although you are unlikely to have to set up a Monte Carlo simulation in the exam, you do need to understand the basis of where this has actually come from to be able to interpret your answers. So consider this example that we have here. The sales and prices charged for product X for each month, along with the corresponding probabilities, are as follows. So we have a number of units that we could actually sell during this period. We may sell 1,000 units, 2,000, 3,000, 4,000 or 5,000 units. And the probability of each one of these 5 events occurring has been calculated as 0.2, 0.25, 0.3, 0.15 and 0.1. So we've worked out that one of these 5 events is going to occur and we have the probabilities of each one. The only problem is maybe we don't know the price that we are going to charge, and we could charge a price of £10, £12 or $14 with the probabilities of 0.25, 0.4 or 0.35. Now we're going to assume here that the price charged and the units sold might be completely independent of each other. It could be the case that the units that we're actually going to be selling, the people have to make decisions well before the price is actually charged. However, the price that we charge may be dependent upon how much it costs us to buy our own raw materials. So just to keep this simple, we're going to assume that these 2 events are completely independent of each other. What we don't know is what the actual result is going to be. And obviously with hindsight, we've got to look back and say, yes, we sold this many, this is the price that we would charge. But when you're trying to predict the future, you'd like to know, what is the expected value of this particular event occurring. One of the things that we won't know for sure is the combination of how these results will turn out. And what is the likelihood of actually getting the highest number of sales, 5,000 units, at the same time as the highest price? Because that is obviously going to generate the highest revenue for your company and will therefore give you the best results. The problem with this, the probability of getting the 5,000 units is actually the lowest probability of all 5 choices, which is 10%. And the probability of getting the highest price is 35%, which is not the highest chance of any of the options available. The other thing you also want to be aware of is what's the possibility of getting your lowest result. Our lowest result is 1,000 units and corresponds at $10. The thing is, although this will represent the highest possible revenue and the lowest possible revenue, what we need to know is what is the likelihood of the high sales and high price occurring at the same time, or the low price and the low sales occurring at the same time. One of the things that we can actually do is generate a simulation model that will predict how likely these things are going to occur, and probably more important, what is the likely amount of revenue we can expect to get if we were to do this on a regular basis. The way that we will do this is to allocate random numbers to the events that we've actually looked at based on their probabilities. Now, random numbers are almost exactly how it sounds, just numbers that you will allocate to these particular events on a random basis. And when I say on a random basis, all we're going to do is take numbers 0 up to 99 and then split them based on the probabilities. So, for example, if we were to look at the units of 1,000 units, they have a probability of 0.2, 20%. So we're going to allocate the first 20% of those numbers to that particular event. So we're going to allocate to it numbers 0 up to 19. And then with the 2,000 units, that has a likelihood of 25%, so we will allocate the next 25% of the numbers to that possibility. And then we're going to repeat that process all the way through on all of those outcomes until we've allocated all 100 numbers. we're then going to do exactly the same thing on sales, on price, and what we're going to have here is a probability of 0.25 for a price of 10, which means that that accounts for 25% of all the events. So we're going to allocate the first 25% of all the numbers, which is number 0 all the way up to 24. Now this seems like a very bizarre process to do. Why are we allocating these numbers to it? Well, what we're trying to demonstrate is the fact that the units are going to be independent to the price. We don't know which combinations we're going to get. All we then need to do is generate random numbers. Well, how do you generate random numbers? Strangely enough, you can actually download random number tables from the internet, or most scientific calculators will actually enable you to generate random numbers, and it will literally produce you usually a 3-number random number, and all we need to do here is ask for a random number, and it would give us the first 3 numbers, and we just need to take the first 2, which will obviously be between 0 and 99. Generate a random number and then look to see which particular category that relates to. For example, if we were looking at the sales units and generated random number 57, from our table that we've actually set up, number 57 falls into that category, and therefore for our first simulation we will take units 3000. We would then generate another random number for the price, let's say random number 98, which would fall into that category for the price of 14. So our first simulation of units and price would give us sales units of 3000, a price of $14, which would give us revenue of $42,000. That would be our first event, and then you'd pick another 2 random numbers for units and price and work out another revenue, another random number for units, another one for price, and just keep generating lots and lots and lots of random numbers and then record all the results. And over a long period of time, more calculations that you actually produce, you would discover that the results calculated would create roughly a normal distribution centered around the mean. And from that we could then work out the average net present value and the standard deviations that actually go with it. One of the problems that we obviously have doing a Monte Carlo simulation is the results that we get are going to be dependent upon the number of simulations that we've actually done. The number of simulations we actually refer to as iterations. So the amount of pairs of information that we actually pick from our random numbers, the more we do, the more likely we are to have a fair spread of the results that we've actually calculated. Now, unless we're actually going to perform 1 million iterations or more to actually work out the results from this, we've got to accept that it might not be incredibly accurate. And one of the things that we could look at to work out the accuracy of this is something called the standard error. Now, the formula for this is 3 multiplied by the standard deviation divided by the square root of the number of iterations. So a relatively straightforward calculation, and it's best to explain what's going on with this with the use of some simple numbers. So if we look at this example, if the expected value of the net present value is a positive $500,000, the standard deviation of the expected value of the NPV is $10,000, and 400 iterations of the simulation model were made to produce these results, what would be the total error in the estimate of the expected value of the net present value? So all we're going to do here is start off with our formula. The error equals 3 multiplied by the standard deviation divided by the square root of the number of iterations. And all we're going to have to do is put the figures in to give us our answer, and then we simply need to interpret the answer. So 3 multiplied by our standard deviation of 10,000 divided by the square root of 400. So 3 times 10,000 is 30,000. The square root of 400 is 20, and if we divide 30,000 by 20, we have 1,500. What this is basically saying, the average net present value that we've created has a likelihood of being wrong of plus or minus 1,500 due to the fact that we only took 400 iterations to create our model. Unsurprisingly, as you'd imagine, the more examples that you take, the more iterations that you include to work out your simulation, the more accurate you would expect it to be. And therefore, if we increased that number of iterations, the figure on the bottom of the calculation would get bigger and bigger and bigger, and therefore your total standard error, based on the number of calculations that you've done, would actually get smaller and smaller and smaller. So in simple terms, the more iterations you can do, the more examples that you can include, the more accurate our final results will be.